Hello guys. Today's video will be about Bitcoin technology, and I'm going to explain you in simple words how it works, what are the underlying technologies, and how do they combine together so that you get these awesome features that Bitcoin has. I studied Bitcoin underlying technology many years ago, and I personally find it really beautiful and interesting. And but yeah, it took me some time to understand how it works, and today I'm going to share with you my current understanding, explaining it on simple metaphors, and showing you each piece on a decent level of detail, so that you will understand how all these combine together and produce this resulting behavior of Bitcoin. So I prepared some good visualizations that will help you to understand how algorithms work without understanding the entire underlying math. So hope it will be helpful to you. And let's start. So we will be on Miro. I have prepared some frames here, and it will move across frames, showing you one piece after another. First thing is that I will show you the agenda, and it will be the following. At first, we will speak about the core value of Bitcoin. How is it different from other preceding technologies that were used for same things? Then I will explain you several basic technologies of Bitcoin: hash, digital signature, decentralized network, proof of work. And then I will, using all this knowledge, I will explain you the Bitcoin algorithm, how it works step by step. And in the end, as a bonus, there will be a review of a real Bitcoin block. I will show you its inner structure, and will show you where you can get it, how you can review it, so that you will be able to analyze it as basically a data set if you want. So let's start. First thing is about the core value of Bitcoin. So to understand the core value of Bitcoin, let's first understand how alternative looks like. And core thing that Bitcoin is about is trust. And classic mechanism of trust creation is like that. We have peers that require trust, for example, like clients in the internet or clients of a bank, and they trust some authority, for example, state or head office of their company or something like that. And this authority writes some data in the database that authority controls, and peers trust the database because they trust the authority. So in this case, authority is needed to produce trust, and peers do not trust each other in such an area. They can trust, but basically some peers may be like attackers, and people may not trust to everybody. Okay, and how does it look like in the case of Bitcoin? In this case, we don't have an authority. Otherwise, we have an area where the blockchain rules or protocol is followed, and peers still don't trust each other, but they follow the protocol, and they write to the database. So some peers may write to the database, all the peers read from the database, and all the peers can validate what is in the database. And because of the protocol is followed, and because of the protocol is mathematically proven, peers trust to the database that is written inside the protocol, and we don't have an authority in this case. And basically, that's it. So we don't have an authority. That's what Bitcoin or other true blockchain projects produce. And in this case, subjects of validation are, for example, hashes. We will speak about them, signatures, proof of work results, and several different things. So that's the things that should be validated are quite formal, and we can just list them. So the core value of the Bitcoin is the trust created without an authority. And if we think about Bitcoin as a currency, of course we understand that there is a big financial bubble around that, but it's not just a bubble. It's a bubble around a good technology which has its core value. And when there is some change on the market and the price drops, it doesn't drop to zero just because there is core value, and the price reflects basically the core value. So it remains. Okay, so let's move forward. That's a piece about the core value. Next one is about one of the underlying technologies, which is hash. So if you already know how hash works, you can just skip this block and go to the next one. But if you don't know, I will explain you what it looks like. So basically it looks like that. You have an input data of any size, for example, like 2 megabytes or even bigger, like a film or 1 gigabyte. This data is given to an input size output, often is 32 bytes or 256 bits. It may be bigger, maybe smaller, but that's a kind of average size of the hash. And this size doesn't depend on the size of the input. But the contents of the hash, of course, depends on the contents of the input. And you can imagine this algorithm as a meat grinder, and you give some meat as an input to that, and it produces you the result, right? And the result depends on what was in the input, but the result is mixed, like quite significantly, so that you cannot understand what was the initial piece that the result is produced from. And if hash algorithm works in the same in the way that if you give the same piece of meat, which means like the same file, the same contents, exactly the same contents, it produces same hash. But if you give a bit different result, so for example, you change 1 pixel here, somewhere here, and you give it as an input to the hash algorithm, the content will be completely different. Not like one simple different, it will be completely different. That's one of the properties of the hash algorithm. And if you give a different piece of meat, it produces still a different result. So hash is a short representation of the input. It's similar to the video thumbnail to some extent. It's theoretically possible to get same hashes from 2 different inputs, but in reality it's almost impossible to find 2 results that produce same hash. You will literally need to brute force all the possible inputs to find 2 that produce same results. And the very important property of the hash is that you cannot say what the input should be to get the hash of the target look. It's not impossible. So the hash algorithm is mixed and confused inside, so that you cannot understand how can you modify the input to get the required output. So you cannot restore the input, and you just cannot you cannot restore the input looking at the output, and you cannot control the output. It's just a kind of random, but it's determined by the input. And of course the input is not destroyed when you calculate the hash, so it's also a difference from meat grinder. And of course, if you think about the meat grinder, you may understand something about the input. If you look at the meat grinder, you may understand, was it meat or were it vegetables, if you look at the results from the actual meat grinder. But hash doesn't allow you to do that. You cannot understand anything about the input looking at the hash. That's its specifics. So it's a very powerful algorithm, and it lies in the underlying layer of the Bitcoin. So we will get back to that later. And let's move forward and look at the second one, which is a digital signature. Digital signature still bases as a hash on some mathematical principle, and on a high level it works like that. You generate a pair of keys, which is a pair of very big numbers, and there is a private key and public key, and they may look like that. So I have an example of private key and public key here. You keep private key secret, and you share public key with everybody. And then when you have some data, for example, a transaction like that, so Alice sends Bob 1 Bitcoin with this fee on a given date, probably some other information. What you do is you calculate hash of this transaction, so that's the hash, and then you sign a hash with the Alice private key and produce a signature. And signing is a kind of some mathematical operation which transforms the hash and produces new short string or new short number similar to hash by length, but different contents. And private key is used to produce this. So basically it's based on the private key and on the hash, and you get some string or some number that represents the signature. And you share the signature with everybody, and then People may use a public key of Alice and may take the transaction, take the signature, and validate that this signature was actually produced by Alice by taking her public key and by checking that the transaction is not modified, so that hash is correct, and thus people are just able to validate that actually Alice authorized this transaction. So it's quite simple on a high level, and only remaining piece is that is this algorithm that lies underneath. If you want to understand it, you can just look through the papers that explain it, but on high level the mechanism is like that. Okay, that's the digital signature. Let's move forward. The next key thing is decentralized network, and I will explain you the difference between centralized and decentralized networks also on an example. So centralized network look like that. You have peers which are connected to some servers, and servers are centers. There may be one server, might be multiple servers, but still there is a big difference between the roles of peers and roles of servers. Servers serve as like central components, and if a server is compromised or shut down or something happens with that, peers cannot work. And servers store data in this case, and they do calculations, and examples of such networks are like Facebook or Miro, the service that I'm currently working in. An alternative to that is decentralized network. That's the architecture where peers are connected to each other. So one peer might be connected to two peers or to three other peers, like maybe to 10 peers, but not to all the peers if the network is big. And there is no single point of failure. So if one peer just is shut down, the network continues to operate, just because there are duplicating connections here, and peers just work with each other directly. And peers make calculations in this case and store the data. And examples of such networks are like torrent networks, or Tor browser, or Bitcoin is also a decentralized network. And a metaphor for that is a net, or a network, where nodes are connected to each other without central component in the architecture. So that's the core tag number 4, and number 3, sorry. And the core tag number 4 is proof of work. I will also explain you how it works. You probably heard about that, and it's quite simple if you understand the hash. So I will show you how it works. So the flow is the following: you or a miner creates a block, which is literally a file with transactions, just a list of transactions. So they have this file. Then they add a random number to this block, like to the contents of this block, and they calculate the block hash. So you remember, the block hash is something which is similar to the results of the meat grinder. And then they check if the hash starts with 10 zeros, like that. And if it doesn't start with 10 zeros or more, they repeat the process again, change the random number inside the block contents, and calculate the hash again, and check if it starts from 10 zeros. If not, they just repeat it and do this over and over and over again. When you heard about like ASICs or video cards that miners do their work on, they do this thing in the loop. They just modify the random number and calculate the hash, and do this over and over and over again, like billions of times. And if, luckily, the hash starts from 10 zeros, then miner just broadcasts this block to other peers using this network or net pattern that we already reviewed. That's it. That's proof of work. So work is in that miner has done all this job finding the proper random number. And it's one of the possible consensus algorithms, and consensus is basically how decentralized network agrees on what is true, like what happened. And proof of work says that thing that is true is this produced block. That's it. The block that has these 10 zeros at the beginning. And because of the hash properties, miner cannot know how to modify the input to get 10 leading zeros. Miner should like randomly check these different random numbers. And because of the task complexity, blocks are generated or mined quite rarely, like not every second. And the number of zeros, is it 10 or more or less, depends on the current power, like how many miners are there in the network. If the number of miners is increased, then the complexity increases and more zeros should be in the beginning of the hash. And if there is a smaller number of miners, then the complexity decreases. Yeah, and this number of zeros is adjusted automatically. It's just programmed inside the Bitcoin algorithm, basically. And complexity of the block generation makes it hard to cheat with transactions, so it takes some time to find this random number and this hash that starts with 0. That's why it's not that easy to find the block and to cheat with the block. We'll speak about it in more detail later. And you can imagine this entire process like digging a mine. So like a businessman may dig a mine without knowing when exactly it will find, let's say, a diamond in there. Maybe like in a second, maybe in a year, and he does some work. And when he finds this diamond and shows it to everybody, people will know that yeah, it likely required a big amount of effort or work for him to find this diamond. Okay, so that's the first technology, and now let's look at the entire Bitcoin algorithm, how it works on a high level. So it starts from somebody to create a wallet in Bitcoin, and wallet is basically a pair of keys, private key which is kept secret, and public key which serves as an address. So Bitcoin address is just the public key of a person. And you may also face a need to create a seed phrase. So when you create a wallet, the application asks you to remember a seed, and this seed can be used to restore the private key. So in this way you can reproduce the same private key in the future if you remember the seed phrase. And what happens next is that, for example, Alice on step 2 wants to send you Bitcoin money, and she creates a transaction. So she writes something like, it basically is done by a client application, and the application writes like, it's from Alice, and Alice address will be here, to Bob address will be here. So for example, you're Bob here. Then she sends 1 Bitcoin with this fee, with this date, so this is a transaction. Then her application calculates the hash of the transaction in the same way as we saw previously during signature creation. So we calculate the hash. The hash is signed using Alice's private key. So here are your pair of keys, and here is Alice's pair of keys. So she uses her private key to sign the transaction, and then Alice sends the transaction to a miner. So I won't stay in detail like how exactly it's done. So she just knows some addresses that she can send the transaction to. So she shares this transaction. And then miner checks the signature. So if this money transfer actually authorized by Alice using her public key, also he checks that Alice has this money on her wallet. So the checks are done, and if it's true, miner includes this transaction in the block that he at the moment is trying to create. And yeah, that's the block. It's just a list of transactions with some additional information, but yeah, it looks like here is the transaction that was added, here are the transactions from other people, and a big list of transactions here. And miner just brute forces the random number with proof of work to get a number of leading zeros that is required at the moment by the algorithm. So he does this work trying to find the random number and to get the corresponding hash. And once it's found, the block is broadcasted to several other peers. So it's like in the net pattern that we said. So here is the new block. And the block contains, besides the transactions, it contains some other information. And for example, it contains a hash of the previous block, like that. And a hash to the previous block works as a kind of link that creates a list or a chain. So chain is created just because next block contains hash of the previous block. That's it. And you see that previous block also contains hash to the previous block, etc., etc., etc. And all these previous blocks are already known to the peers in the network. so that new one that is created is just shared with the other peers, and they check that, okay, yeah, this block is created correctly. I see the required numbers of zeros in the beginning, so I take this block, add it to the head of the chain, and start to create the next block. So other miners start attempts to create the new block from this moment, using this one as a previous now. So that's it. So nothing magical here. Several simple technologies combined together, and they result in this awesome feature that we have in the Bitcoin. And let's review some properties of that. So for example, if there are several blocks that are created at once, some miners continue with one branch of the chain and some continue with the other. And the rule is that the longer chain is selected. So if some group of miners produces second block, then the other group of miners just accept this alternative branch because it's longer. But it happens rarely because of the time needed for proof of work. If proof of work will be very simple and blocks will be produced every second, then yeah, there will be lots of collisions. But Bitcoin algorithm is adjusted in a way that blocks are produced on average once per 10 minutes, and this time is quite enough for the block to spread across the network in majority of situations. Attacker cannot modify the transactions or blocks because of the hash. So if some number will be changed, like for example, attacker will say like, you sent me not 1 Bitcoin but 10 Bitcoins, he will need to modify something in a block and somehow spread this block across the network. But it's not possible because hashes are calculated, and if you change anything in the content, then the entire chain will become incorrect, because all the consecutive blocks depend on the previous block because they include the hash of the previous block. And attacker cannot spend somebody else's money because of the signature, so he should know the private key of a person to spend money. So again, signature protect the money. Attacker cannot shut down any central component in the network because there is no central component. So if he attacks several computers, remaining computers will still operate, and he will need to attack the majority of nodes so that he will be able to compromise the network somehow. And attacker generally cannot change blocks deep in the blockchain. For example, say, okay, I will create an alternative branch starting from some deep block and create a longer chain in parallel. It's hard to do because the deeper the block in the network, the more power will be needed for an attacker to mine quicker than the network does. And you know that at the moment there are many miners and lots of electricity is spent on that. An attacker will need to operate better than that, so it will consume tremendous amount of resources. And all the logic, these rules of this protocol is implemented inside the Bitcoin core, like in the code. And this code is embedded in the mining software or in the software of full node wallets that contain the entire chain. So they are not like taken from some server, they are just in the application, and this code is open and you can just go to GitHub and review it. So that's how it is implemented. And as a result, yeah, you get this feature of trust created because the protocol enforces it without any authority, just because people follow that and people are motivated to follow the protocol, and yeah, trust creates out of it. So that's the main part of my talk, and in a second I will tell you and show you the bonus thing. And before that, I ask you to press like to this video and subscribe to my channel so you will get notified about new videos that I will create. And now let's get to this bonus part. I will show you what it looks like actually. You probably already seen the transactions and blocks in the Block Explorer, but I will show you the structure of this data so that you can download it by yourself and just play with it. So first thing is that there is an API, for example, on blockchain.com, a free and open API that allows you to download transactions or blocks. And there is there are multiple endpoints here, and one of the endpoint here is a raw block. Here is it. So you just open this URL with a raw block and provide a block hash here, and there is an endpoint also that allows you to get hashes of blocks on particular day, so it will allow you to download the blockchain if you want, and you will get the results. So let me show you what it looks like. So here is an example of API call. It takes some time to open the page because the block weighs several megabytes. And here in this form, the block looks like a JSON. In reality, the block is in a binary format, but for the simplicity of work, like if you want to analyze the data, it's better to work in JSON. It has almost the same structure, but it's just easier for you to parse it in your code if you want. So, and what I will do is I will save the page as a JSON file. Yeah. Now I can open it using an editor and see. So here is the information, and here is the block hash. Actually, it's not contained in the block because it can be calculated. Then there are several like other fields. Won't speak about all of them, but here is a field that I was speaking about previously, the previous block hash. Here is it. So several fields here. And here we have an array of transactions. Usually the first transaction is a transaction produced by the miner, where miner gives himself the reward, the newly mined bitcoins attributed to him. And transactions looks like that. You have inputs, and in the case of first block there may be no inputs at all. For first transaction, sorry, there may be no inputs at all, but they will be some output. And here is the output where the mined money are attributed to the miner, and here is the address of the miner. And other transactions are transactions when some people send money to other people, and we will definitely see inputs here, at least one. So some input here. Here is the information about the wallet from. Here is it, address. Here is the information about the value. Where is it? Yeah, here is it. So that's how many bitcoins are sent, and this is number in Satoshi. Satoshi is 1 divided by 100 million of Bitcoin. So you can divide this by 100 million. And yeah, it's still quite a big amount, like more than 1 Bitcoin is sent here. There is information about commission here, about the fee here, and yeah, some other information. And all the blocks and all the transactions look like that, so the same structure. And if you want to play with it as a data set, you can just download it through API and just parse it and use it. So here is it. I hope this video will help you to understand the Bitcoin technology better. If you have questions, please write them in the comments. If there will be many questions, I will probably create one more video explaining them, because I haven't covered things like how transactions are sent to the network, or like how some specific aspects of proof of work like what is the difference between older and newer Bitcoin protocol versions, etc., etc., etc. So if you have questions, write them in the comment. And for now, thank you and bye.